Welcome to the solutions to the Regents Physics Kinematics problem set, problems number 20 and 21. Let's jump right in here and get started. How far does a plane fly? So that's D. Label that with a D. That's what we're looking for. In 15 seconds, T, while its velocity is changing from 145 meters per second, that has to be its initial velocity, to 75 meters per second, final velocity, at a uniform rate of acceleration. So we do know that it's accelerating, but we don't know the value. Okay? All right, we're looking for D, given initial velocity, final velocity, and time. Because the object is accelerating, we cannot calculate the distance traveled without knowing the acceleration. So this is a two-part problem, a two-step problem, and we have to start by finding the acceleration and then use that acceleration to find the distance. Well, that leaves us with VI, VF, and T, and we're looking for A. We go to the reference table to make a selection here for an equation, and it looks like to find A that we would use VF equals VI plus AT. VF is 75 meters per second. VI is 145 meters per second plus A times, and the time is 15 seconds. Equation, substitution with units. We now go ahead and algebraically solve for A. You take whatever steps you need to accomplish that. Pause the video to do the calculation, and then checking your answer, you should get A to be negative 4.67 meters per second squared. Okay? All right. We did not express that answer to 2 digits because of our time, because this is not our final answer. And we only want our final answer to 2 digits, so we're going to hold off on that until we're done here. Okay, so we've got our acceleration. Now we can go ahead and use any choice of motion equation that has A in it here. I think any one of them would work to find the distance. Probably the easiest one would be D equals VIT plus 1/2 AT squared. Our negative acceleration makes sense because clearly the plane is slowing down, so it should have negative acceleration. Substituting, we go D equals, and our initial velocity was 145 meters per second for 15 seconds, plus 1/2 negative 4.67 meters per second squared times 15 seconds squared. Go ahead and do the calculation, however many steps you need to. Pause the video and check in your answer. You should get D equals 1.6 times 10 to the third meters to 2 digits. All right, so 2 steps to do that. I'm actually going to pause here a moment and extend this question. I'm going to show you how this question could have been done much more quickly and without doing both steps here. We can use V equals D over T to solve for D here in this problem, if we remember that this V is average velocity. What that means is that if we take the average of 145 and 75, now we would take the average of that, we would add them together and divide by 2. But that would be the distance divided by the 15 seconds. Go ahead and solve for D doing this, and we get 1,650 meters. To 2 digits would be 1,700 meters. Okay? So we could have gotten this answer in 1 step, what it took us in 2. You might be asking, well, why the difference in the answer here? 1.6, that seems like 100 meters is a big difference. First of all, remember this is sig figs, 2 digits. Our worst measurement here is the seconds measurement. And because of the sig figs used in the 2-step problem above in red, we got a 1.6 times 10 to the third meters. And because of the sig figs down in the green calculation, it gives us a slightly different answer. We're not going to get too worried about that. Okay, let's move on to number 21. Engineers are developing new types of guns that might someday be used to launch satellites as if they were bullets. One such gun can give a small object a velocity of 3.5 kilometers per second. That would be the final velocity the object attains, because if it gives the small object that velocity, that means the initial velocity had to have been 0. And our indication here is that the gun can give the small object the velocity, so VI equals 0. Moving it through only 2 centimeters. All right, so there's your D value. They want the acceleration the gun gives the object, and over what time interval does the acceleration take place. The first thing we have to address here is that we have some non-standard units for both our final velocity and our distance. So let's go ahead and address that. VF at 3.5 kilometers per second. Let's get that into meters per second. So our kilometers goes in the denominator to cancel the meters. To cancel the kilometers. And 1 kilometer is 10 to the third meters. So kilometers cancels, and this would be 3.5 times 10 to the third meters per second. All right, so that's standard units for that. Then let's go take care of our D value. We've got 2 centimeters there. We need to have that be in meters. Centimeters goes in the bottom to cancel, meters in the top. And 1 centimeter is 10 to the negative 2 meters. Centimeters cancels. 2.0 times 10 to the negative 2 meters. All right, so we're ready to proceed with a question. And A says, what acceleration does the gun give this object? So we know the initial velocity is 0, the final velocity we now have, the D value we have, and we're looking for A. So for part A, if we go to the reference table and select the equation that matches up to the given information, looking for A here, looks like we would choose VF squared equals VI squared plus 2AD. Substituting 3.5 times 10 to the third meters per second. We have to square that. Plus, not plus, equals. Our initial velocity is 0. So VI squared would be 0 squared plus 2A, and our distance is 2 times 10 to the negative 2 meters. Solve this algebraically for A. Pause the video if you need time. Take as many steps as you need to be accurate here. And you should get an answer that's 3.1 times 10 to the 8th meters per second squared. An incredible acceleration. Okay? For part B, over what time interval, so we're looking for the time over which the acceleration takes place. All right, so we're looking for T. Now that we know A, it looks like the easiest choice for our equation would be VF equals VI plus AT. VF again, 3.5 times 10 to the third meters per second. VI is 0 plus A, 3.1 times 10 to the 8th meters per second squared times T. We go ahead and solve for T. Again, pause if you need time. Take as many steps as you need. And t is 1.1 times 10 to the negative fifth seconds. So an incredible acceleration over a very short amount of time, which makes sense based on the information given to us in the problem. All right, more to come with more practice on one-dimensional motion calculations in class.